Okay, thanks. Thanks for having me here. I really appreciate it. I have to acknowledge my co-authors in this. Laser is this one. So Jordan was an undergraduate at Cal Poly in San Luis Obispo working in the STAR program, STEM teacher and researcher program at Cal Poly, and Jackie Coburn from the University of Guelph in Canada. Without their contributions, I wouldn't have been able to do this at all. So we're going to talk today about spectral content variations in the sun, as Judith has pointed out, and see if we can see those effects on Earth. So can we see anything, can we see the effects of changes in spectral content of the sun on the surface of the Earth? So here's a picture from the Solar Dynamics Observatory showing UV picture of the sun, and just to demonstrate that there are plenty of things happening on the sun in the UV. So on all time scales probably, and I borrowed this from one of Judith's previous publications showing changes in the spectral content of the sun. So on the y-axis, on the y-axis would be the percent change between the gray line, I think, is the one that we want to follow here, the percent change through a solar cycle, right? So between solar maximum and solar minimum. And so you'll notice Kevin Z is going to appreciate all of this stuff down in the extreme ultraviolet, right? That is, maybe these pulses are throwing up xenon, right? So you get a lot of changes through a solar cycle, on the order of 100% change down there in the EUV, there near 100 nanometers. So EUV doesn't make it to the Earth's surface, it all gets absorbed. So I put, and Judith did the same thing, this transmission curve then, and I put a little crossing point there at the 50% transmission line, and to see how much change is there in the emission from the sun in the wavelengths that might make it down to the surface of the Earth. So there's on the orders approaching 1% in there, changes in UV radiation, UVA radiation anyway, through a solar cycle. And so my quest here, some might call it a blind obsession, but can I see that at the surface of the Earth? Right? Is there any effect down here at the surface? Certainly up in the upper atmosphere. In the upper atmosphere, we're going to see a lot of changes, as Judith has already done a great job of showing us. Can I see this at the surface? And so that was my quest. And so the first thing I did was try to say, hey, do we have any data measuring UV at the surface of the Earth? And indeed we do. So I have to thank Germar Bernhard of the Biospherical Instruments down in San Diego, who helped me access this data from an NSF program. Anyway, showing then this is, I think, at 380 nanometers. So, just sort of right in the middle of UVA there. And, you can see the annual cycle, and what's not shown there, this is, sub-daily data. And so there's the daily cycle in there and the annual cycle. But, my eye wanted to find out, what are these longer term variations there, and do they relate to a solar cycle? So that's my question. And so there's the sunspot number, and I could probably use some other proxies, but, I notice maybe that there's some correlation visually anyway. We could do some other things, but in my blind obsession, I'm thinking, well, maybe, okay, maybe. Now there's a whole lot of other things that affect the interannual variability of UV radiation reaching the surface from the sun. And in particular, ozone is one of those things. But Victoria talked about changes in cloud cover. Well, so clouds obviously affect the transmission of UV radiation to the surface, and so changes in cloud cover over these longer term cycles might affect this interannual variability as well. Interestingly, in recent studies, people have connected the emission, UV emission, reaching the stratosphere to cloud nucleation. And so you might think, as Victoria pointed out, that we might have some changes in cloud cover through geologic time as changes in the UV radiation from the sun reaching the Earth have occurred. So that's one thought anyway. Many things that are affecting the interannual variability. And so could it be that these changes in UV are being directly influenced by solar cycles? I don't know. I'm intrigued, but I'm not convinced. But let's plod forward, since this is a blind obsession. You might think that, you know, the easiest place to look for this would be near the poles, where maybe the atmosphere is thinner and drier and maybe a little bit less ozone to absorb. And so, you know, I thought, well, if we're going to see something, maybe we see it at the poles. And so another reference here from Malinka shows that on the x-axis here is wavelength, and we're down here into the UVA, and on the y-axis is albedo. And properties of some surface snow and ice indicate that the albedo decreases as you move into UV wavelengths, right? And so I thought, well, the albedo is decreasing into UV wavelengths, and UV intensity is changing. Might there be some connection there? So if you think about this, if I put more UV radiation onto the ice and the albedo there is lower, then the spectrally integrated albedo is lower if you add UV, right? That is, a higher proportion of the incoming radiation will be absorbed if more of it is in the UV. And so the combined effect of those two things would be a lower effective albedo of that ice. And so let's see if that works. Well, we did a little bit of a model. We did a meltwater model with a convectional component and a radiation component, and I modified the albedo to be able to vary it a little bit with the phase of the sun, the phase of the solar cycle. And so in this particular model, we get a 5% reduction in effective albedo, doubles the meltwater production. Now, we wouldn't see a 5% reduction, but, you know, more on the order of less than 1%, but still there's some effect there that we might have to take, you know, that we can consider. And so as a case study, I sent Jordan around looking for a whole bunch of VARV sequences in the literature. Now, a VARV is an annual sediment, right? We'll talk about that in just a sec. But this is Iceberg Lake in Alaska, right? Iceberg Lake. And it was a lake that was fed by several small glaciers. Almost all of the input to Iceberg Lake was from those glaciers. And in an annual cycle, during the summertime, there would be some meltwater feeding Iceberg Lake, and in the wintertime, it would be frozen over. And so you can envision maybe at the bottom of Iceberg Lake that during the summer months, some water is rushing in there and bringing some, you know, larger sediments in. And during the wintertime, when it's frozen over, well, no meltwater is coming in at all, and there will be some fine sediments that settle out of the water column, and you might have these annual layers. Now, those annual layers are called varves, right? This sedimentary structure where you can see annually resolved sediments. And so Iceberg Lake, actually it melted. One of the places that was damming up Iceberg Lake melted, and it completely emptied. And so some researchers went through, Diedrich and Lasso went through and collected some sediment cores. Now, those sediment cores were varve sediments, and so you can count back the years one by one. And Diedrich and Lasso measured the thicknesses of those varves. And you would expect maybe during a warm summer that more sediment would flow in and you would make a thicker varve, and during a colder summer or a cooler summer that you would have less sediment and a thinner layer. And so you might envision that the thickness of those layers through time would reflect interannual climate variability. And so here we look at two time series. The one time series is the thickness of those varves in Iceberg Lake back to about 1610, and the second one is our proxy for solar activity, which might be the sunspot group number in this case. And you know, again, in my blind obsession, I noticed some sort of correlation, especially in the latter stages, from that record between the sunspot record and the VARV thickness. Now, if you go to the reference, we provide a whole lot more measures of, you know, numeric measures of correlation that indicate that the visual correlation we see in the graph is highly unlikely to be the result of a chance association between those two signals. And so there is something to explain here, some sort of correlation to explain there. And beyond that, beyond just the correlation in the time series signals, we looked at the spectral content. Now on the left-hand graph here, in cycles per year, this is the Schwab cycle for the solar period, and it's the main short period signal in the solar cycle. We look at the same signal in the VARVs here, and we see that there's a little bit of power enhancement above those confidence intervals there, and you wonder if that's what's happening, if the sun is forcing those things. Here's the spectrogram, and you'll also notice this is the sunspot cycle here. That's the spectrogram increasing here, and this is the VARV cycle. You see the Maunder and Dalton minimums fairly clearly there. And you know, based on arguments made in the reference, you can at least be intrigued, I hope, that solar cycles are directly causing those variations in the surface ice. And so here's some conclusions. It looks probable that solar activity directly affected the variations in thickness at Iceberg Lake. And so maybe we should think about accounting for solar activity when we think about what are the factors that melt ice, especially near the poles. And you know, this effect would be greater if there were less ozone in the atmosphere. So anything that people do to reduce the ozone concentration in the atmosphere would exacerbate the melting near the poles. So there's one possibility. The picture in the background, one of the things that's not listed here, the picture in the background is a picture of a VARV sequence from the Gauganda Formation, Paleoproterozoic, so where's Sunny? We looked at this VARV sequence and saw a solar cycle in there as well, or a putative solar cycle. And so maybe, if this is right, if this analysis is correct, then the solar cycle in the Paleoproterozoic was 10 years also, right, since these are annually resolved layers from about 2.3 billion years ago. So anyway, there's a conclusion that's not listed there. If this analysis is correct, maybe we can infer something about solar variability an awful long time ago. Thank you.
I might just speak and without my. Oh, thank you.
Gary, thank you. Very nice work. My question is the glaciation formed, I said, is by the increased slow fall, and if it exceeded the slow melting and need glaciers. And you were talking the UVs, the photons. In solar wind, solar cycles, they have host of ionizing particles, and positrons, electrons, alpha, beta, muons came out. And what impact could you comment on that, caused by the ionizing particles slow falling?
Well, I'm not sure about ionizing particles, you know, at the surface, right? In our analysis suggests that it's a direct result of UV radiation impinging upon the ice, right? Melting more ice during a solar maximum than during a solar minimum. And so, you know, I'm not sure what you know, ionizing particles might do there. Certainly, there are all sorts of things that contribute to variability of melting ice.
There's no data. Couldn't find any reference.
I'm not sure. I can't point to anything that I know of in the literature. Sorry.
Have you thought about, well, there's the Pacific decadal oscillation, which is also decadal, and that will has a projection up on the Aleutian High, you know, and so will affect weather patterns up there. Have you thought that perhaps this is just you're in your periodogram or your wavelets that you're just really seeing a PDO signal?
Okay, so you know, correlation doesn't prove causation, right? And so you want to look beyond correlation. And so one of the things that we did was in Southeast Alaska there, we took some climate records, temperature, for instance. We did temperature, we did precipitation, we did wind, right? And we did the same periodograms for those climate variables, at least those three. And out there in that 10-year Schwab periodicity, flat, absolutely nothing, right? And so it doesn't preclude the idea that climate could be affecting those VARVs, okay, on other timescales, or even amongst that timescale if there's some nonlinear interaction that's happening there. But it makes it a whole lot more difficult to have climate explain the periodicity, the increased amplitude in that Schwab periodicity.